Hi, everyone. I'm Young Kim in Geography, and I'm the coordinator of the Wealth and Poverty theme. And thanks for coming to the Wealth and Poverty Week on Global Challenges event. Can you hear me? Good. Okay, then today, we are having presenter from Geography too. Dr. Ryan Fogt is an associate professor in the Department of Geography here at Ohio University, and he's also the director of the Scalia Lab for Atmospheric Analysis. That is the only on-campus meteorology lab used for teaching, research, and weather forecasting. His research interests span a wide range of topics on climate variability and change, with particular focus on Antarctica. That's very exciting. And Dr. Pope that teaches courses on meteorology and atmospheric dynamics, and his teaching excellence was recognized formally and officially when he received the honor of the university professor last year, right? Okay, and so that's really good. And one more thing, this is for announcement. As I said before, this is a Wealth and Poverty event, so those who are interested in Wealth and Poverty theme activity, you may pick up this thing from the table. And some of you might be interested in Wealth and Poverty certificate, the certificate curriculum, and how it overlaps with your own majors. You may pick up these things. So without further ado, I will let you hear from Dr. Paul.
Okay. Well, I'm excited to be here and excited to talk to all of you about climate change. It's something I'm very passionate about. Just a reminder for those that are in the CAS 14-15 class that I will have some after 11 for you to talk about. So when people leave at 11:30, you should stay around for just a little bit and we'll talk a little bit more, okay? I have talked about climate change a lot of times to a lot of different audiences, from high school to even kids, elementary kids, to college campuses. And I've always found it's easier to talk about climate change after a big heat spell. People tend to be a little bit more persuasive, at least more convinced that climate change is happening after we've had some warm weather. And luckily, I mean, taking today out of that picture, we've been in a heat spell lately. Parkersburg, West Virginia is our closest weather reporting station that has over 100 years of data. And I've been tracking since August 1st their high temperatures, the maximum temperature for the day. And this is the average plotted here on the graph. It's normally 85 in early August, and then it funnels down to about, right now, about 74, 75 is what we should be experiencing for our high temperature of the day in late September. Here's the record high temperature line. It goes up above 100 a couple times, but it's usually upper 90s. 2015 was a pretty normal year. This is the chart showing you that temperatures were above average quite a bit and below average quite a bit. We had a few days where we didn't even get out of 75 for the high last year in August and in September. 2016, a lot different looking than that. This is 2016 here in blue. In fact, we only had 6 days in the last almost 2 months where we actually fell below the average, below average high temperatures. We've had a prolonged period of above average temperatures, and in fact, we tied or broke the record at Parkersburg twice in this period. Now, good way to look at this persistent heat is through an idea called cooling degree days. And these are just looking at how much warmer your average temperature is from 65 degrees Fahrenheit. And then they sum up. So if we sum that up since August 1st, the black is the average. You can see it peaks up, and then it kind of levels off once the average temperatures start really not being much above 65 anymore. 2015, again, in purple, really close to the average. 2016, increasing heat every single day. Because we were above average in our average temperatures as well as our maximum temperatures, we added more and more and more and more cooling degree days to this year, and we've kind of continued to increase with very warm August conditions and leading that into September as well. Zooming out to the U.S., Ohio is not alone in this. Many of the mid-Atlantic states, Pennsylvania, New York, the eastern seaboard here, the number 122 tells you that that's the warmest year for August average temperatures across the state in 122 years. So record warm for them. Ohio, we're the third warmest, 120, but east of the Mississippi, almost everywhere experiencing much average temperatures. You can even zoom out a little bit more in a second, but I want to show you the time series of Ohio temperatures first, show you that There's a lot of variability in August. We were the third warmest August in 2016, but there have been previous Augusts that have been warmer. There's a slight upward trend. It's not very large and not very impressive. Yes. Move it up a little more. Better? All right. I'm being video recorded, so make sure that people want to hear me at home or yes, they're watching. My wife should be tuning in, so now she can actually hear me. She tunes me out most of the time, so. All right. Anyways, back to Ohio in August here. A lot of variability. So the upward trend in temperatures in August exists, but it's not terribly impressive. If we zoom out and look at the globe, August in 2016 was above average almost everywhere. The record warmth that we saw in the mid-Atlantic states extended into the Gulf, or into the Atlantic Ocean, parts of southern Africa and Asia, northern Asia as well as kind of Southeast Asia and Central Asia, the Tibetan Plateau in that area, all above average in record conditions in August. So it was not just Ohio, and it was not just the mid-Atlantic states that experienced a really warm conditions in August. Much of the globe was warmer than average. And if we put that into a time series, it could look like this. Globally average temperatures, northern hemisphere and southern hemisphere. This is just the month of August, the mean temperature, average across the planet or in those hemispheres. And 2016 in August, just ever so slightly, topped out 2015 in August. And it was the 16th consecutive month where we've had record warm conditions average across the planet. Really, really impressive, continually warm conditions in August that have persisted now for 16 months. So you can go back over a year and find each month before that had set a new record globally average temperatures. Pretty impressive warmth. But that's not really climate change. Climate change is not one single month. We have to look at all months and across all regions to really understand the picture of climate change. So I'm going to zoom out and look across all the year and look at temperatures there. So we're going to look at this warming that we have in August and place it in a larger context. Here are globally average temperatures starting in 1880 and going to 2015. These are annual means, so we're averaging from the whole calendar year, January through December. And the early part of the late 19th and early 20th century was marked by colder than average temperatures, these blue bars. We had a period of relatively warm conditions in the early 40s, cooler and mild, near normal in the 50s, 60s, and early 70s. And then since the late 70s, we've been on this upward trend. 2014 was a pretty impressive year when it finished. We thought that was a very warm year. Right here, 2015 shattered that. Globally average 2015 was much, much warmer than any year that we've seen since 1880. When we started really taking measurements of temperature globally. And of course, that made headlines in January, right after it broke. NASA scientists, NOAA scientists said 2015 is the warmest year on record. Over 100 years of data, 2015 blew it out of the water. It looked like this. Actually, it was a horse race that never actually came back in second. And it started out fast and warm and stayed warm. Compared to the 6 other warmest years on record, 2014 snuck up at the end and just became the warmest year in November and December. 2015 didn't even have any surprises. It was warm all year round and never looked back. It was warm all year. Now you might be wondering, what's 2016 looking like in this context? Well, here we go. It's scary, isn't it? 2016 compared to 2015, which blew the other 6 years out of the water, is way above those. It peaked in March and has been going down slightly since El Nino has decreased in intensity in the tropical Pacific, and that really makes the world a lot warmer place. But we're still above 2015. Our forecast, these are just 2 possible forecasts, and these are actually very, very conservative forecasts of what 2016 might finish out to be. The circles here, we're saying our average temperatures across the globe are going to match the long-term average. That has not happened in the last 30 years. Okay, that means basically there's the same amount of cold places as there are warm places across the planet, and they all average out to be the average temperature for that particular month. Very, very unlikely that's going to happen. The other one, which actually shows more cooling, is also very unlikely to happen. This is basically going to match temperatures in 1998. Now you might ask, why 1998? 97-98 was a very strong El Nino year. We just finished a long, strong El Nino in 2015 through early 2016. And 1998 would be like the kind of the analog for that. We had a really warm year in 98 on average. But what happens here, this one, is that 1998 then shifted to this pattern called La Nina, which is very, very strong, and actually works to make the temperatures across the globe colder when that pattern develops. Unfortunately for this year, La Nina is probably not going to happen. We thought it might at the end of the El Nino cycle, but forecasts now show that there's going to be a neutral pattern in the tropical Pacific sea surface temperatures, and therefore unlikely to have a La Nina event, and likely to have that cooling globally that would happen with that La Nina event. So both of these forecasts, which, by the way, either show a tie with 2015 or just below it, are unlikely to prove true. In fact, I'm pretty confident that 2016 is going to be the next new record of annual mean temperatures that's going to show above 2015 and be quite impressive in terms of the long-term change. Now, if we look at temperature trends across the planet, where are we seeing warming happening the most rapidly? This plot shows you surface temperature changes from 1901 through 2012. The reds are warming. The purples are warming. It's everywhere. The dots, the black circles in those little shaded boxes, indicate where that trend is meaningful in a statistical sense. In other words, it rises above the natural variability, the noise in the climate system, if you will. And that happens almost ubiquitously across the whole planet. There are a few places in the Pacific and down here near Antarctica where we don't see much warming. By the way, the white areas are just where we don't have a long enough data record to provide a century-length climate change temperature trend signal. The only place that it's cooling is in the North Atlantic. You might be excited. Yes, at some places it's surviving. It's not warming yet. That is actually expected to happen in a warming world. We're expected the North Atlantic to become colder for reasons related to the ocean circulation. So it's not actually a good thing. It's actually a sign that there's actually warming still going on. Warming is most marked in the Arctic and the high latitudes of the northern hemisphere, where over the last century we've seen warming over 2 degrees centigrade. That's our threshold, we think, for global average temperatures. If we rise above a 2 degrees centigrade threshold, we've reached a point where there will be some major changes across the planet, and changes that could actually be very life-threatening. Certainly not, maybe not for all human life, but certainly for plant and animal communities that have much more challenge to adapt and resist those changes. To show you some of those things that we've seen, I want to show some pictures. I think pictures are worth 1,000 words, and sometimes they're better than the data that I've shown you. These are some things that have happened recently in response to these warming trends. Things like Antarctic glaciers melting. This is the Pine Island Glacier. It's one of the most rapidly moving glaciers on the planet right now. It's decreased its volume quite rapidly, and this is just one snapshot of a calving event where ice is broken off of this glacier. This ice sits on land, so when it breaks off into the ocean, it adds sea level. It melts and will raise global sea levels. This glacier is deemed to be unstoppable, and it's melting from below. It's nothing to do with the atmosphere and it's warming. It's actually warm water getting underneath the ocean, underneath the glacier, and causing almost probably irreversible ice loss. We're seeing ice loss in other places. This is a high latitude glacier, work done by people at Ohio State. They've been back to this place almost every single year and took a photograph in the same location. The Coriolis Glacier used to come down to this basin here. It's now retreated much farther back. This is all a melt pond that sits there, showing dramatic change in the landscape in just a fairly short period of time. This glacier provides a lot of freshwater supply for people in Peru, and it's alarming that it's decreasing quite rapidly. In Tanzania, the Kilimanjaro ice cap has changed its size quite remarkably. In just a 7-year period here, we've seen its size go down more than half. And it won't probably be around much longer. Now this is Glacier National Park, bring it a little closer to home. Don't focus on these white things, those are clouds. You might get excited about them. But these blue dots here are the glaciers that are there. This is a false infrared satellite image, 1984. The extent of these glaciers is quite dramatic. It's large enough to cover most of the mountain peaks. Recently in 2015, much of those glaciers are much smaller. Some of them are completely missing. The reds that you see over there are actually damage from forest fires. Another image of change, perhaps related to climate change. All these glaciers in the Glacier National Park are expected to be gone by 2030. So it won't be a great place to go see glaciers anymore. We've also seen water levels decrease, both in freshwater and saltwater bodies inland. This is the Aral Sea in Central Asia. Its volume has decreased dramatically due to warmer conditions and more evaporation. This is also happening in Utah with the Great Salt Lake. And in Alaska, ecologists call these things drunken trees. The permafrost has melted so much, it's a solid ground that holds the trees firm and their root structures firm to a vertical position. It's melted so much that the ground has become more soggy, loose, and the trees are no longer stable and they start falling over and leaning. This has happened in the last 30 years. We've seen a big change in Alaskan ecosystem structures related to climate change. Underlying all these things are population changes. Population changes are one of the forces that drive climate change due to increased emissions of greenhouse gases as communities grow and expand. Just one image here of Manila in the Philippines showing rapid expansion of the population over a fairly short period of time. So why are all these things happening? Why is the climate changing? Why is the Earth warming? And why are all these ecosystems and land covers changing in response to that? Okay. Well, let me first present you to this idea called the Anthropogenic Argument. Okay. Anthropogenic is a fancy word for meaning human caused, human generated. And it works like this. The sun's up high in the sky, nice thing, and it sends out energy to the Earth. It's a shortwave radiation, high frequency energy from the sun, that hits the Earth's surface and starts to warm the Earth's surface. Right? But the Earth is much, much colder than the surface of the sun. Right? And so because it's colder than the surface of the sun, it's going to emit energy, radiation out at a different intensity, at a different frequency or wavelength than the sun's energy. And that energy goes back into the sky from the Earth's surface. And as it's going back through the sky, it encounters these gases, which I'm representing by dots here. They're actually gases. Okay? These are the greenhouse gases. Things like carbon dioxide, water vapor, methane, nitrous oxide. They're all very, very effective at taking that energy released by the Earth and absorbing it, taking it in. And as they absorb that radiation, they start to warm up. And when they become warm enough, they'll start to release their own radiation, part of which gets sent back to the Earth's surface. We call counter-radiation, radiation from the sky. And that would lead to warming. This whole thing I've told you right now has another thing that's related to it, and that's the fact that the energy from the sun, these short waves, largely get through the atmosphere. It's only the ultraviolet parts of the solar spectrum of energy that get absorbed. The ultraviolet gets absorbed by ozone in the stratosphere. It's a very good thing that that happens. It keeps skin cancer at bay and other harmful diseases related to too much energy from the sun. That's really high frequency energy. But largely that all gets in. So the atmosphere is pretty transparent. So it can get in freely, has more challenge getting out because of a different wavelength. This is the greenhouse effect. Raise your hand if you think this is a good thing. A few of you. Is a very good thing. Okay? The greenhouse effect, as this stands right here, is important for life as we know it. If we didn't have those gases in our atmosphere, all the energy coming in would basically be able to get out more freely, and a planet would be a lot colder. The globally average temperature would be below freezing. Right now we sit at a comfortable 58 or so, annually average, globally average. It would be below freezing, and plant life and ecosystem dynamics would be completely different, and we'd be living in a much more harsh planet. So this is a good thing. The greenhouse effect works the same way that your car does in a hot summer day. Energy from the sun travels through the glasses and windshields in your car, heats the car up, all right? But the energy coming out of your car is at a longer wavelength, and so it can't go back out as quickly through the glass, and your car warms up rapidly. Right? What we're doing to the atmosphere is what's alarming in this. We're enhancing the whole greenhouse effect by adding more of these gases, adding more carbon dioxide, methane, nitrous oxide, and perhaps water vapor to the system. Adding more of those gases means more that things can trap that radiation and send more of it back down, and it leads to more warming at the Earth's surface. Now, I'm sure you know that we're increasing carbon dioxide. This is a plot from one of the best observatories of carbon dioxide in Hawaii. There's a seasonal cycle to carbon dioxide. It peaks in May and is the lowest in the late fall, early winter, related to the biological life cycles of the northern hemisphere. We've reached our peak in May here last time of over 407 parts per million. When I started teaching here at OU, we were not even close to 400. We're in the 390 range. Now we're above 400 consistently. But you can look further back into time. This is just a plot showing you average carbon dioxide concentrations from various sources. And around 1750 or so AD, we've seen a big spike in these things where the growth has been exponential on this time scale. We can even go back farther into time. This is from an ice core in Antarctica. The time axis is reversed on the top, 0 back to 800,000 years, almost a million years. And the carbon dioxide curve is the middle curve here in green. And how does this work? Well, we have these ice cores that look like this, remember? They have these annual layers. You can see them really clearly here, clear to opaque layers that reflect changes in the accumulation from year to year. And so we can actually count back in time when that ice core was formed and that layer was formed. Now, if you look a little more closely at the ice core, you see these little irregularities in them, these little blotches. Those are actually gas bubbles that are trapped in the ice, largely. So as the ice is freezing, it traps the air around it with it. And that air can be sampled as we melt the ice core. So we can actually go back in time and get a really good history of these gases from these ice cores. That's what they did here. So if you go back in the ice core, you can actually get almost a million years of data from this one ice core in Antarctica. Here's the carbon dioxide curve. It fluctuates in the last million years or so from around 180 parts per million at its lowest to around 200, maybe 300, 290, 300 parts per million at its highest, naturally. Now, if you look at the bottom plot here, this is temperature measured in Antarctica from a different chemical in the ice core. And these two are very strongly positively correlated. When one goes up, the other one goes up. In fact, if you were to reproduce the bottom temperature curve, slide it on top of the carbon dioxide curve, they basically trace each other. Now, as a scientist working with data, this is the best correlation you're going to ever see. You're not going to see any climate data that's ever this strongly correlated. So there's a really strong relationship here between carbon dioxide in these ice cores and temperature. Now, what causes those changes in carbon dioxide and therefore the changes in temperature? Well, it's actually this top curve. If you look at the timing of the peaks in this curve, and there's a lag of about 50 to 100,000 years, 50,000 years or so, you'll see that there's a minimum in carbon dioxide and a minimum in temperature. This top curve has a nice frequency of about 100,000 years. So it peaks about every 100,000 years. And it's what we call the eccentricity of Earth's orbit. It's a measure of how circular is the Earth taking around the sun. In times when it peaks like this, the Earth's orbit is more circular, more like an oval, less circular, more eccentric. And at that time, with a lag of cooling, a lag of so many years, we'll see cooling going on across the planet. What's happening essentially is that when the Earth's orbit is more eccentric, more like an oval, we'll spend a short period of time really close to the sun, when the gravitational pull from the sun is really strong. But that gravitational pull essentially flings the Earth out at a farther distance away. And a farther distance from the sun means less radiation from the sun and a colder planet. That cycle continues on for about 50,000 years and leads to a dramatic cooling of the planet and actually forms the ice ages that we see, cycle back and forth. We're currently in a period of the Earth's orbit becoming less eccentric, more circular, which would lead to warming naturally as we change the Earth-Sun geometry. And if we were to take carbon dioxide for today and place it on this scale from the ice core, we'd be up there. 407.7 parts per million CO2 in May. Off the charts. Nothing even comparably close to that value. If you've watched Al Gore's Inconvenient Truth movie, he gets on a ladder that rises up just to place the current value of carbon dioxide in context of an ice core. It's ridiculous. It's really, really high. Now, I can't prove to you that carbon dioxide physically is causing the warming. Even though we know it leads to warming, we have to use tools to show that the carbon dioxide is in fact causing the warming. That's where climate models come in. Climate models are very effective tools that show us what is doing what in terms of the climate system. They allow us to actually isolate processes and variables like carbon dioxide and their role in global climate change. Now, they're very complicated things. Climate models are not weather forecasting models. So if you think weather forecasting models are always wrong, that doesn't mean climate models are necessarily. Okay? They're very complicated but very beautiful things. They simulate all the processes that we see on the natural Earth, in the ocean, on the land, on the ice, and in the atmosphere, and communicate back and forth through a series of equations, through a series of model code. And they basically come to a solution that looks like this. This is 1 month from a US climate model showing you water vapor concentrations. You can think of it as clouds. It's not really, but it's like that. A lot of moisture here in the tropics. Look at this nice typhoon spinning up here into Asia. Low pressures moving across the US. Storms that cycle down into the Southern Ocean around Antarctica. What's beautiful about this is that there's no line of code to tell it when and how to make all these things work. It works on physical laws and produces a climate, a version of Earth that looks really close to ours. This is not Earth in the sense that this August, simulated by the model, is probably never going to perfectly match any August ever. But it looks close enough. These processes do happen in August. We do see these mean conditions exist in August in such a way that they have quite a bit of skill. We can look a little bit closer at them and see how well do they actually perform. One of the ways to do that is to compare it to data. So here in black are globally average temperatures that I showed you at the beginning of the talk. Each one of those little colored lines is a climate model simulation. Now, none of them perfectly match the black, but if you average them all together, which is an important thing to do, the red curve here, the thick red curve, matches the black much closer. Okay? And in particular, these vertical lines here, Krakatoa, Santa Maria, Agung, El Chichon, Pinatubo, are volcanic eruptions, and we put those into the model at their time that they occur, and the model responds to those with cooling, just like the Earth does. So you can see, in particular, after these big, powerful winds here, the Earth goes through a little bit of a cooling cycle after a volcanic eruption. The models get that. They reproduce the warming pretty well. There's been some debate about the over-prediction of warming in the last 15 years. That's sometimes called the climate hiatus or climate pause. I won't have time to talk about that today, but if you have questions about it, I'd be happy to answer them later. And they're the only tool that we can really use to look back into time as what was causing the changes, and then, of course, look forward into time. The IPCC even comes out and says, formal climate change attribution, understanding what caused what. Those studies are carried out using controlled experiments with climate models. And the model responses to specific forcings are often called the fingerprints of those forcings. So in other words, we can actually look at each of these gases individually and their fingerprint on the climate. What are they doing to the climate? How are they changing the balance of energy in the system? Up here are the well-mixed, long-lived greenhouse gases, shorter, more localized greenhouse gases here, and then some other factors, including clouds and aerosols, and then their signature. Basically, if it's to the right, it's leading to a warming signal. We can isolate that in the model. If it's to the left, it's a cooling. Carbon dioxide is the biggest warming mechanism right now, in part because it's much more abundant than methane and nitrous oxide. And so we see a warming signal from that that matches what we're seeing on the planet pretty well. In fact, these other things here that lead to warming are basically offset by aerosols and cloud changes that lead to cooling across the planet. So carbon dioxide comes out to be the main player, and a climate model helps us understand that much better. But what I like is this slide. I want to pause a little bit and go a little more slower on this one because this is the one that convinces me of the role of carbon dioxide more than anything else. In these models, we can play around with them and run them in a world where there was no carbon dioxide change. We can run them in a world that basically has carbon dioxide staying at a constant concentration throughout time and see what the model does in response to that. We call that the natural forcings run only. It basically has everything that happens naturally without human influence in it. That would be the bottom curve here on the left. The black is the observed temperature going up. Of course, The blue and the red are two different generations of climate models. Neither one of them show warming at the end. So there's a lot of variability that's happening naturally here, but by the end of the 20th century, we do not see either of them reproduce the warming trend. Now we can do the other way around. We can say, let's just add in the anthropogenic factors, the greenhouse gas increases, carbon dioxide being the biggest one of those, and see what the response is there. And the red curve shows a dramatic warming that's actually a lot larger than the observed black temperature trend that we see there. Put the two together, the cooling introduced by natural variability and the anthropogenic warming gives you this top plot, which we showed you in the previous slide, matches up pretty well. What does this tell me? We need the greenhouse gases in the model to reproduce the warming. The absence of their increase does not at all reproduce warming in the world. It kind of wows me. It says, wow, this is the factor. This is what's causing the change, the greenhouse gases. The models make it pretty convincing. And there's a lot more data that I could show you that come up with the same conclusion. Here's one. Natural forcing alone, blue, weak warming to cooling. Here, this is the observed thing we're seeing actually happening over this time period. Natural plus the anthropogenic changes in greenhouse gases match the observed. Natural warming by itself, nothing. We can do this on different areas. So over land and ocean, combined, the blue is the natural, no warming trend. We need both. We need the greenhouse gases there. And we can run it over into every single continent one by one and see. Yes, there's warming going on almost every single place. We need greenhouse gases to explain that warming. If we do not have greenhouse gases increasing, we do not have a warming trend. Obviously, in the real world, we have that warming trend. So greenhouse gases are a big player. Now, the future. Climate model is the only way that we can look forward into time, and the story is not good. The blue is an optimistic scenario, the RCP 2.6. Don't worry about what that means, but it's basically a scenario that says we're going to stop emitting greenhouse gases and remain at a constant volume or a constant concentration in the atmosphere as of the year 2000. There's thermal inertia that exists in the atmosphere, so we're going to have a little bit of warming afterwards. But what the good news about this simulation is, this right here is a 2 degrees centigrade threshold. We stay below that in all the simulations. The red and pink are the RCP 8.5 scenario, what I call and most climate modelers call the business as usual scenario, which basically means we live as we have been living and we don't change much of anything. No international policy to change or regulate greenhouse gases and other things, and we just continue to pollute. In that scenario, we see a warming that's well above the 2 degrees centigrade threshold by all the models in the range. And an average warming on the order of 3 to 5 degrees centigrade, depending on what model you look at. Well beyond the concern threshold of 2 degrees. It's not equal everywhere, just like the warming trend is not equal everywhere. So this is the reduced emissions scenario. Excuse me, this is the business as usual scenario on the right, the more likely scenario perhaps. Warming everywhere, largest in the Arctic. In the business as usual scenario, the trends and changes are alarming. We're looking at changes over 9 degrees Celsius, about 20 degrees Fahrenheit. Much, much warmer due to feedbacks that exist naturally there between the ocean and the atmosphere. Across much of the US, we're seeing warmings that are going to be above 5. So what once was an 80-degree day is now a 90-degree day. And these persistent patterns of warm conditions in August and early September could become the new normal, rather than that nice change that we see at this time of early fall. So by the numbers, we're seeing a projected increase from 3 degrees to upwards of 6 degrees, more in the Arctic than over mid-latitudes. And this warming can have dramatic impacts, which I'm not going to have time to talk to you about too much today, but we've already seen some of those in the images of change that I showed you earlier. So what did the IPCC conclude? This is the governing body of climate experts worldwide. And they write a report every so often. The most recent one was in 2013. And they said that it's extremely likely, more than 99% chance, that more than half of this warming that we're seeing going on is caused by the anthropogenic increase of greenhouse gases. We're to blame. Our activities and choices are the problem. And we're polluting the atmosphere in such a way that's leading to more than half of this warming, which is pretty sad news. But I don't end there. I want to provide a little bit of hope. Because if we're part of the problem, or if we are the problem, that means we have the power to be the solution. So I want to talk to you on hope here at the end on various scales. Why I'm not completely depressed every day I come to work. Okay? Why I'm trying to hold on to something that gives me something to look forward to. On a global scale, this paper came out at the end of the year, last year, and it said 2015 emissions were actually slightly lower than in 2014, which was really interesting. And they said despite economic growth across the planet, which is normally when we see reductions in emissions, when the world has a crisis and there's not much economic growth, we see a reduction in emissions those years. But we had none of that really. We had still large economic growth, and we saw a reduction in emissions. It looks like this. This is the CO2 emissions globally average, and gigatons of carbon per year. This is a measure of economic activity. Basically, if it's going down in this scale, that we're seeing growth in the economy. And 2015 fell just slightly from 2014 in total carbon emitted that year. And that was in a time of economic growth. And it made me excited. It made me a little hopeful. And the story here is about a 0.6% change, not a large change, but it's not a big growth for once, which is good. And that comes out mostly from China. If you're breaking it down by countries, India still continues to increase. The rest of the world is increasing, apart from these places that are examined here individually. Above this black line is increases still. So China is still increasing in the emissions they're having, but the rate of increase went down, and quite dramatically from 2014 to 2015. The US, by the way, has actually been decreasing its carbon dioxide emissions in the last 10 years almost. It's actually not as bad as you might think. Now, it's not as good as the European Union, which has been much more aggressive, and they've decreased their emissions much more effectively than the US. Why has China decreased? There was a big shift in China in 2015 in terms of where they did their energy production. This shows you where they're getting their energy from: coal, oil, natural gas, nuclear, hydro, and other renewables. And then the brackets here show you the change in the growth rates from this 4-year period, 2010 to 2014. Coal is still the dominant way of China's energy, but its change is very, very small over the last 4 years. It only grew about 3%. Meanwhile, half the growth in the energy production came from clean sources: nuclear, renewables, including hydropower. And the other renewables, wind and particularly solar, really grew a lot. Almost a third of the energy production growth came from these renewable clean sources of energy. And that makes me optimistic. The future of the world in terms of carbon dioxide emissions is largely banking on China and India right now. The US too, but those are the bigger polluters, and we're seeing a need for these changes like this to happen. It really depends on what's going to happen in the future if China keeps going in this direction, how much carbon dioxide is going to be emitted. This is without policy, by the way. There's no law, regulation in China, like Kyoto, to regulate how much carbon dioxide is emitted. Zooming into the US, kind of gave away a little bit here, but we've also been a little bit better than I would have thought of. Electricity, transportation, and industry are the main sources of carbon dioxide emissions in the US. I'm just going to focus on energy just to be comparable to what we're seeing in China. And our energy production, electricity production, is largely coal still. Coal is our biggest source. This is 2014 numbers. I'll provide you some more recent numbers in a little bit. Natural gas is about a third. And then we're seeing smaller percentages here of the other ones. Other renewables, apart from wind and solar, would be lumped up here in about 3%. Solar at 2014 was less than 1% of our energy production. But that's changed. We've seen a big shift in the US in our energy production. I think largely due to the good administration changing the way we produce energy. And coal has gone down. For every job there is in coal right now in the US, there are 3 new jobs in solar. 3 new jobs in a clean source of energy. It gives me some hope. Hydropower has remained relatively neutral. Non-renewable hydro has grown in the US. This comes in the form of wind and most commonly solar power. Solar power has expanded quite a bit in the last 10 years. And we see that actually even happening locally here in Athens with multiple solar companies providing ways to produce energy much more cleanly than with coal or natural gas. Our CO2 emissions since 2008 have gone down almost 1 trillion metric tons, which is a big decrease. I'm not sure if it'll stay that way, but it's really encouraging that we're seeing a decrease. Now, the devil's in the detail here. I have to be completely transparent. It's not all good news. I'm hopeful, but it's not all good news, and that's because of this. Natural gas has been increasing as far as in energy production. This is related to fracking. I'm not a big fan of that. It's good that it's cleaner. Less carbon dioxide is emitted from that process than from coal combustion, but it has lots of other environmental concerns that are not really the greatest solution either. But we've seen carbon dioxide go down. So there's some hope in the US. I want to close by bringing this down to a personal level and making it hope on your level. Because some of these things are out of your control. You really can't control all of US policy. I doubt you can control international policy by yourself. But you can do some things. This is a picture of my kids. This is Anna here and Abigail on the left. Their personalities are perfectly reflected in this picture. Anna, she's kind of like our princess. She loves getting into clothes and fashion already at age 8. Abigail here, you can see she's a spitfire. She's full of energy and she's off the wall sometimes, but she's just a beautiful person in her own way. Not a day goes by that I don't think about their future. And I don't mean like just racism and all the social issues that are causing this planet to be a scary place. I worry about their climate future. I worry about what world they're going to be in 10, 20, 30 years. And I worry about my grandkids. It's a scary place. But I believe there's hope still for me and for them on an individual level. I haven't given up yet. You see, I like to view the world this way. We live in a world where there's multiple stressors. Social, environmental stressors, physical stressors on us each day. And as we go through our lives, we're going to be reaching decision points where we have choices that we can make that can make us more vulnerable to those stressors or less vulnerable and more resilient. Every day. And my plea and my hope for you on an individual level is when you come to those choices in life, that you will make choices that lead you and this world then into a more resilient space. How can you do that? Here are some ideas. First and foremost, avoid this destructive pattern of thinking that nothing is going to ever matter. Yeah, this is a global problem. It's a huge problem. The scale of it is intense. But if you keep thinking that nothing is going to ever change and you can't do anything about it at all, hopelessness is not going to be effective. Choose hope. Choose action. Choose concern for the environment over despair. Really important to be active and less complacent in these sorts of things. How can you do that? Back to the 3 models that you may have heard many times before. Reduce, reuse, and recycle. I talked recently in another class, and another student said refuse is another one. Just don't get it. Don't buy it. Don't consume. Okay? Which I liked as well, you know? Reduce your waste. Use things over again, multiple times. Coffee cups, bags at the grocery store. Simple things where you're reducing your individual impact. And then things that you can't save or reuse again, if you have to throw it out, recycle it if you can. Don't just put it to a landfill where it can release methane and destroy the groundwater systems. Recycle. Be climate conscious. Transportation and energy are 2 main sectors of the US that produce emissions. While we can wait for a policy to regulate these are things that we actually have a lot of control on a personal level in terms of our impact. We can make choices in our transportation to carpool, to ride our bikes or walk, much more. Now, I'm not saying I'm perfect at these things. I do live out of town, but I try to share rides and carpool with my wife as much as possible. Energy usage. If you're not using it, turn it off. Don't leave things plugged in that aren't having a need. Don't consume more energy than you need. Reduce your consumption of energy. Big coming up right now. Vote for the people that have environmental values and positions that you do, that have the same concern for our humanity and our planet as you do. This election is going to be very, very big for this at the national scale. The two candidates could not be farther apart on this issue of climate change and our environmental stewardship. There will be people outside today, if you're not registered to vote, that can help you to get registered to vote and be active in this process. But please vote for the people that have environmental issues. And that does not even mean just presidents of the United States. It means state and local officials as well. Live simply and locally. A lot of energy and transport use is for cycling in things for you or making more. Part of the problem with climate change is consumption. And we're consuming more, especially in the Western world, than we perhaps need. So living simply, less is more. And locally, buying food at farmers markets or local produce can help reduce your impact as well. I don't have time to show data on this, but there's a study that shows if you're actively involved in a civic organization concerned about the environment, you are almost certified to believe that human activity is causing climate change. It's the biggest predictor of your belief in the cause of climate change in the US. Not true for all the other countries, but in the US, if you want to know if human activity is causing climate change, find out if they're involved in an organization. Get active and be involved in plenty of organizations here on campus to really promote this sort of thing. And last, I'm a firm believer in this. Studies have also shown that education and awareness really help to inform the public and really help to make a difference. Take what you've heard today, use it for your family, use it for your friends, and use it for those around you to help to lead to a more environmentally sustainable and friendly future for all of us. Okay, thank you.
Thanks a lot. And any questions?
Convinced you all?
I have a question.
Yeah.
Okay, go ahead, Brett.
A lot of the evidence for the relationship, the causal effect between carbon dioxide and climate change is historic, looking at the relationship between temperature and the presence of carbon in the atmosphere. I understand how you get the carbon dioxide from the ice cores. How do they know what the temperature was to match those up?
Yep. So they use oxygen isotope ratios. O16 and O18, the sampling and the ratio of those two in the ice core can be related to temperature and precipitation. And so they can go back into them and just use the oxygen as a way to get temperature.
From both carbon dioxide and
So it's two different, yeah, carbon dioxide is different gas than oxygen, so they use both of those differently for different things.
okay.
Yep.
That's what I meant.
Yep.
You mentioned how actual temperature is less than the prediction for a period of time. Would you explain more about that now?
Yeah. So the climate pause period. And it's easier to show the graphic again, so I'm just going to scroll back to that. You can humor me for a second here. So this is actually something that skeptics fed on quite a bit when this report was reached in 2013, that the warming trend from about 1998 through early 2000s reduced quite a bit, and the model showed a lot more warming. And they basically said the models are all wrong. You can't trust them. And so we can't trust them for the past, we can't trust them for the future, and they're too sensitive. But this pattern of actually being different has occurred in the past before, on order of about 10 to 15 year scales. What we see happening is there are times when natural variability in the climate system can produce patterns that lead to less warming. This whole period from 1998 to 2013 was marked by a pattern that we know as the Pacific Decadal Oscillation, and it actually made the Earth's temperatures colder. And it was a natural pattern that exists in the oceans, in the North Pacific Ocean, and led to changes in the jet streams and other factors that made the planet relatively cold. We also had more La Nina events that tend to make the Earth colder during that period than El Niños. There are not very many strong El Niños, and so that really reduced the warming. That has broken down since 2014. 2014, we saw the shift of that climate pattern and resurgence of El Niños, this last major El Niño being one of those, which released more heat from the ocean into the atmosphere, and we saw that 2014 be the warmest, and now 2015 by far the warmest, and 2016 likely to be the next warmest. So that period of natural variability that kind of kept us cool for a while has broken, and we're going to see a lot more warming going on from there. Follow-on question?
Yeah. When we see global cooling trends, is it just because the Earth is somehow, it's still sinking in the same amount of energy, right? It's just somehow hidden from our...
It's being stored in the ocean.
Okay.
Yeah, below the ocean surface. So it's buffered, it's delayed. And a lot of that heat was released during this El Nino event. Came up from below the ocean surface to the ocean surface, and then supplied the atmosphere with heat and made the Earth a lot warmer in 2014 and 2015.
So in a lot of ways, this data we're recording isn't actually how much energy the Earth is absorbing. It's just what we're seeing on the surface.
Yeah, well, there's not been very much change in the energy end. So the energy from the sun cycles just slightly from sunspots and its distance, but those things haven't changed much. And so the energy in has basically been the same. It's just where is it placed in the Earth atmosphere, ocean system, that changes. And those things happen naturally.
Thank you.
Yep. Yes?
How do you feel about geoengineering?
Good question. There are some brilliant solutions. Geoengineering is basically ways that we can alter a new climate. We can engineer a new climate, a new Earth. There are some great ideas. Planting trees is one of those simple things, right? That we can just reduce the carbon footprint. There are some crazy ones, like put mirrors in space. Launch mirrors so that they could orbit around the Earth and reflect the energy coming in. Most of the bad ideas for geoengineering work on the shortwave radiation, basically letting less energy come in. And I do not feel that's an all-effective solution. It's not the energy in that's the problem. It's the energy going out that's the problem. And we need to reduce the energy going out. We need to actually increase the energy going out, and not change the energy coming in. So the engineering solutions that are focused on the shortwave are more like a Band-Aid, and actually in a Band-Aid that's not going to really solve the problem. But the ones that are focused on reducing, in an environmentally friendly way, reducing the trapped energy in the atmosphere, so allowing more to go out, those are the ones that I think have promise. So there are good and bad solutions, but most of them are kind of crazy, unfortunately. I don't feel like, that's the best solution. I think reducing our emissions are the best ways to go forward in that one. Yes?
How do you feel about nuclear energy?
I'm a fan of it in some ways. It's certainly very clean, and clean in the sense of carbon and gases that get emitted from it. There are other environmental concerns with nuclear, so it's not a perfect picture. Some countries in Europe, like Germany, have really adapted more nuclear as their source of power and seen some positive results, but there's always this concern of things with the waste and the reactors and everything else that you have to be very quick to monitor, and it could be a major issue if those things went wrong. But I feel like the trend for things, because nuclear actually has been very flat, it hasn't really grown. We're seeing much more changes in the other renewables like wind and solar, which I think are the wave of the future. And if we can catch more onto those, which do not have much environmental concern, I think we're moving in the right direction.
Question. You talked about the coal consumption in the U.S. and other developed countries has declined, so that has caused the international price of coal has gone down because the demand has gone down. So that has allowed, indeed, developing countries in Asia these days, industrializing countries in Asia, so they are the ones who are really consuming coal. So indeed, the declining international price of coal has allowed those Asian countries to hold on to coal because the price has gone down.
Yeah. That's a challenge with climate change, is there's not an easy solution because it's an economic and political thing all at once, as well as an environmental thing. And there's not a win-for-all solution with any of these things. There will be losers and there will be winners. But even in the current state that we're in right now, there are losers and there are winners. And unfortunately, we're in a world right now that the losers that are most suffering from climate change are the ones that are least responsible for it. The developing world, the world that has less means to adapt or to be resilient to climate change based on their lifestyles and their income, they are much more vulnerable, and they're the ones that are least responsible in terms of their emissions of carbon dioxide. So yeah, the economic stuff is well beyond my knowledge, but there are definitely issues that are tied in with the change of the coal industry globally that are related to that as well, for sure. Okay.
Any other questions? Thanks a lot.